Okay, so now I want to talk about solving rational equations. And here we're going to use that technique that we used with fractions earlier on in the semester and also with complex fractions earlier this week. We're going to use the LCD or the LCM to remove essentially the fraction part of the equation and then solve the equation in an ordinary way. Now, occasionally we'll get something like a polynomial that has that's more than just a linear equation, and so you'll have to use the zero product principle to solve that. Remember, that's where you factor something, and in order for that equation to be solved, one of the factors has to be zero. So we essentially find the zeros of that. So let me take you through a few of these examples, and I'll have you do one or two. And the easiest case is when we have constant denominators. Okay, I think we've even done this earlier this year. But let me show you the method with the LCD or the LCM. LCD is the lowest common divisor, and LCM is least common multiple, so it's numerically the same thing. So we're going to multiply both sides by 12. And you can see that instead of multiplying, first divide. So you got 12 divided by 6 is 2, so it's 2 times x minus 3. And then 12 times 7 is 84. 12 times x over 12 is going to be just x. And so then we extend our parentheses, and then we solve the linear equation, and we get x equals 30. And you can put the 30 in the equation to test it out if you want. Sometimes that works out to be more work than actually doing the solutions, so you're probably better off just really carefully checking your arithmetic. Okay, so let's put a variable in the denominator. What's that? Yeah. I know I talk 4 times as fast as you write, right? Okay, how's that? All right, so let's put a variable in the denominator, and this is something we haven't seen before. So this is where this technique really starts to help. On something like this, you might be tempted to find a common denominator and then cross multiply and do all sorts of things, and sometimes that works, and sometimes it's a little too complicated for that. So the easy way to do it is to first find the LCD. And in this case, it's just 3x, right? That would be the common denominator if we made a common denominator with both sides. Okay, so that's going to be 3x. So we're going to multiply both sides by 3x. And so in that first 3x times 8 over 3, the 3's cancel and we get 8x. And then on the second part, 3x times 7 over x is just 21 because the x's cancel. And then minus 1 over 3x times 3x is 1. Okay, so here we have a straightaway equation now, no ratios. And so 8x equals 20. And so x equals 20 over 8, and we reduce that to 5 halves. And again, we'll keep with the principle of using reduced improper fractions. Okay, so here's one for you to try. Try using this method where you identify what the LCM is, and then or the LCD, and then multiply through to end up with an equation without ratios. So what's the LCM? I think Natalie said it. It was 2 times y plus 5. And so we're going to multiply both sides by 2 times y plus 5. And so then when we multiply 2 times y plus 5 times 12 over y plus 5. You see the y plus 5's cancel, and I'm left with 2 times 12. And then I'm going to multiply 2 times y plus 5 times 1/2, and so the 2's cancel, and I just get a y plus 5. And then I have 2 times 2 times y plus 5, so I have 4 times y plus 5. Now at this point, then what you do is now you remove your parentheses, you do all your distribution because you don't have any fractions anymore, and you do need to collect all the variable terms on one side and all the constant terms on the other. So from here we simplify both sides. We see that y plus 29 equals 4y plus 20, and so we subtract 20 from both sides and subtract y from both sides, and we get y equals 3. Okay, and this one is easy to check if you can look at just the black to see where we are. It's 12 over 8 plus 1/2, so that's going to be 4 halves. So we have 12 halves, or excuse me, 12 eighths plus 4 eighths is going to be, I'm not doing this in my head right, 8 twelfths plus 1/2 is going to be 2. All right, so that works. Okay, so now let me show you something. Checking your answers, like I said, sometimes is a good thing to do. Sometimes it's more work than it's worth. But one of the things that we should be aware of is that it's possible to have no solution with these kinds of equations. And one of the ways that you get a no solution is that you have something impossible, like -2 equals 0, or something like that, where your x's drop out and you have something that's not true, 5 equals 3, or something of that sort. The other way has to do with domain restrictions. So let's do this one in the conventional way. The LCD is x minus 2, so I'm going to multiply both sides by x minus 2. And so I get 5x on one side, and 7 times x minus 2 plus 10. The x minus 2's cancel in that second one. And then when I expand this, I get 5x equals 7x minus 14 plus 10. And then further simplify it. The -14 plus 10 is -4. Subtract 7x from both sides, and I get -2x equals -4, or x equals 2. Now what's wrong here?
It's x minus 2 on the bottom.
Yeah, we get x minus 2 in the bottom. So here, it's not really a function, so we don't have a domain per se, but we still want to do the same thing that we do when we put it in a domain restriction. We want to exclude certain values from our potential solutions, so we're not dividing by 0. Okay, so demonstrate that. We get 2 minus 2. And so here you have, it causes division by 0, so it's not a solution. So this one has no solution. And this is relatively easy to check now, because what you want is you don't want your LCD to be ever equal to 0. So don't even, well, you can look at the equation here, but a reliable way to look at that is look at your LCD, because that will have all the factors that could make that equation potentially some term divisible by 0, or division by 0, I should say.
So would you like to say something in this problem?
No solution.
Just say no solution.
No solution. Okay, so now I want to give one more example, and here's an example where we're going to have more than one solution. Everything that I've shown you so far reduces down to a linear equation, which by the characteristic of a linear equation has exactly one solution or no solutions. So here's one that's relatively straightforward. We're going to pick our LCD as x plus 1, and we'll multiply both sides by x plus 1. And you see what happens here. On the left-hand side, the x plus 1's cancel, but when I multiply these two, I actually get a quadratic equation here. Okay, so when I multiply through by the 4, I get this 4x squared plus 12x plus 8. Now I'm going to subtract x and subtract 8 from both sides, and I get 0 equals 11x, and the 8's canceled, right? 8 minus 8 is 0. Okay, so this is what I mean by solving by the zero product principle. We know that this factors now. It factors into x times 4x plus 11. So we have two possible solutions. We have x equals 0 or x equals negative 11 over 4. Because that's what makes either of these two factors 0. And so, indeed, we have two solutions here. And so it's possible that you have any number of solutions depending on the degree of what you end up with. And so that's certainly a possibility, even though it looks like we only have linear terms in the original equation.